Hello, I'd like to update you on our work applying artificial intelligence to right whales. My name is Kristen Khan and I'm with NOAA Fisheries, but this work has been a monumental undertaking with researchers and data scientists around the world, and I will touch on several different projects underway. I fly with the Northeast Fisheries Science Center aerial survey team to monitor the abundance and distribution of right whales. The photographs we take on these surveys are matched to the North Atlantic right whale catalog and form the basis for mark recapture estimates of abundance, along with many other important research efforts. The use of AI for photo identification of right whales began with the Kaggle competition in 2015 to automate the classification of individuals from aerial photographs. We collaborated with the winning team, DeepSense AI, to publish the results of their deep learning approach in 2018. And then in 2019, just before our last right whale consortium meeting, the winning deep learning algorithms from DeepSense AI were retrained and deployed on Flukebook for North Atlantic right whale aerial photographs. You can now access the automated matching system directly from the North Atlantic right whale catalog website. And the system was expanded to southern right whales in April of 2020 with catalogs from South Africa, New Zealand, Australia, Argentina, Brazil, and Chile. As expected, accuracy for southern right whales was considerably lower at 26% top one accuracy compared to 61.3% for the North Atlantic. Future research is anticipated to make the algorithms more generalizable so that the southern right whale model can more closely approach the North Atlantic model in accuracy. Machine learning is underway to expand the capacity of the system to recognize whales from lateral vessel-based photographs. WildMe has achieved some impressive results on these challenging images with background subtraction and a state-of-the-art machine learning algorithm named Pi for pose invariant embeddings. This novel approach is achieving 55% top one accuracy and 80% top five accuracy on the database of around 3,600 left side head images. This work to be able to match whales based on multiple features and from multiple different perspectives is really pushing the boundary on what is possible in automated wildlife identification. NOAA is also exploring AI for gray whale photo ID in work led by Trevor Joyce. NOAA's West Coast Regional Office, along with the Southwest Fisheries Science Center and the Bureau of Ocean Energy Management, funded a collaborative effort with WildMe to evaluate how well some of their existing and newly developed computer vision tools perform on matching gray whales. I'd also like to tell you about a new project that we recently launched to explore the feasibility of an operational whale detection system using satellite imagery in collaboration with the Naval Research Laboratory and the Bureau of Ocean Energy Management. Detection of marine mammals from satellite imagery was not possible until the launch of the IKONOS satellite in 1999, and IBELA demonstrated the initial proof of concept for detecting whales from space using IKONOS imagery to detect captive orca whales and wild humpback whales in Hawaii. In 2014, Fretwell used a WorldView 2 satellite image with 50 centimeter panchromatic resolution to identify and count southern right whales in cloud-free, calm water conditions. They concluded that it was unlikely that they could differentiate different baleen whale species with the resolution of the currently available satellite data. Satellite detection of whales became more feasible with the launch of Maxar's WorldView 3 satellite in 2014. And several studies have demonstrated the technological feasibility of detecting whales from space. In 2018, Cubanes manually detected 4 species of whales, fin, humpback, southern right, and gray whales with pan-sharpened WorldView 3 satellite imagery with 31 centimeter panchromatic resolution. Resolution has drastically increased and whales are now clearly identifiable, including details such as fins and flukes. However, manual methods took about 3 hours and 20 minutes just for 100 square kilometers, which is clearly not sustainable for detecting whales at an operational scale. The 2019 paper by Borowitz et al. Showed the ability to detect whales using convolutional neural networks, using a standard ResNet and DenseNet architecture on downsampled aerial images of minke whales, and then tested on WorldView 3 very high-resolution satellite imagery. The best model correctly classified tiles as either containing whales or only water. This is an exciting development because obviously machine learning algorithms are a precursor to an operational system. At our last consortium meeting, Olivia Pisano presented her PhD project. She aims to develop an automated census method using very high-resolution satellite imagery and deep learning algorithms to automatically detect, identify, and count whales in the Gulf of St. Lawrence. So, all of this seminal research has been building up over the years into something that is beginning to look like we could take it out of academia and into production. At the last Marine Mammal Conference in Barcelona, there was a workshop on the detection of marine mammals from very high-resolution satellite imagery, and the room was abuzz with the possibilities that this holds for understanding worldwide marine mammal distribution and abundance someday. There are also two big developments with the satellite company Maxar that really caught my attention. One is the WorldView 3 Legion program, which launches next year and will have a revisit rate of up to 15 times per day and the capacity to collect data over open water at the same 30 centimeter resolution as WorldView 3, a truly impressive scale of image collection on the horizon. The other infrastructure in place to support the operational usage of very high-resolution satellite imagery is their geospatial big data platform, which is a cloud data storage interface where you can access WorldView 3 imagery stored in the cloud on Amazon Web Services and process machine learning algorithms using Docker without ever having to download and visually inspect the imagery. Accessing data in the cloud would alleviate the time and burden of downloading these large image files. Now, while all these developments have been ramping up in recent years and becoming ever more tempting, access to the imagery at a large scale has been a significant obstacle to progress. We basically want worldwide coverage of the highest resolution commercially available satellite imagery at an affordable price, and no surprise, this isn't possible. However, we have found a mechanism in collaboration with BOEM, USGS, and the National Geospatial Intelligence Agency to acquire some imagery at a meaningful scale. Very high-resolution satellite imagery from WorldView 2 and WorldView 3 satellites have been tasked over seasonal aggregations of North Atlantic right whales and the Cook Inlet beluga, and work has begun on automating the workflow with a variety of Python scripts to query Maxar's imagery database, address sun glint phenomenon and band offset, tile, and detect objects of interest via spectral statistics. There are significant obstacles ahead, and it remains to be seen whether or not satellite imagery can truly be used operationally for whale detection. But we are beginning to lay some of the groundwork to evaluate the possibility. And I'm happy to chat further about this work or answer any questions if you'd like to shoot me an email. Thank you.